Hello guys, I'm sorry that 2 weeks before today there was no video. Unfortunately, I was lying sick in bed. Let's start with today's video, where we are looking into locking inside of async methods. You just wrote this cool async function that does some asynchronous work. And now you want to ensure that only one thread is calling it at the same time. So you have two tasks in this example where you call this Google endpoint. But when you try to lock around it, you get an error. You can't compile. Cannot await in the body of a lock statement. But why is that? As you might know, when locking an object, this lock belongs to that thread that was currently running when locking. So when we look at another function, this function here is exactly the same, except for these two lines here, where we get the current managed thread ID. Before the get async call and after the async call. Let's debug this. As you can see here, before the get async call it was managed thread ID 7 and after the call it was thread ID 9. So that means it's now another thread that is executing the continuation after the get async. If we were in a lock statement here, this thread number 7 would have to release the lock and somehow give it to thread number 9, which in turn sounds like a race condition. And this is why, or this is one reason why a lock and await are not compatible. Of course, if you can't use lock and await at the same time, what can you do if you want to do something like this? Well, you can use the semaphore slim, which we have here, that we initialize with initial count 1 and max count 1. So it behaves more or less like a lock. Before we call this get async, instead of locking, we await this await async call from the semaphore. And in the end, we release it again. And because this semaphore has an initial count of 1, it will decrement it to 0, and every other thread that tries to wait on this semaphore will have to wait until it is more than 0, which happens when we release the semaphore in the finally block. And the max count is 1 because in the release you could provide an argument with a release count, for example 5, and then this semaphore would be at 5. So then 5 threads would be able to enter this try block, but we don't want to do that. That's why we have this max count of 1. Another thing that is quite popular is the Nito.AsyncEx NuGet package, which has an async lock. And this one I find quite interesting, and I looked into it, how it works, and I'd like to show this to you. But first, let me show you the usage. Instead of a try finally, you have this using block, which of course, when lowered, is a try finally block, but it's pretty nice to read here. And inside the using, await this lock async call. And inside this using block, you just have the code that you want to run at most once at the same time. Now, how does it work? This is really interesting. Let's look inside the lock async function, where we see this request lock async, which in turn has a lock object, but this is only for internal thread synchronization. What is interesting is it is using a lock and it is async, but only the name is async. The function itself is not async. That's why it is able to use this lock statement. Anyway, if it enters this function, it looks if it is taken already. If not, it sets it to true and just returns this key with this as an argument, which is just some holder object which implements iDisposable. We will look into that in a bit. And if it is already taken, it enqueues this on a queue. So this in turn returns a task, which then, when it will be signaled, it can continue with something. So let's look at the dispose of this key object. Here you can see in the dispose, it releases the lock of this context object, and the context is the async lock itself. And then if the queue is empty, that means it was the last thing this async lock should do, then it sets taken to false. Otherwise, it dequeues the latest item and provides a new key object with the async lock as an argument. And if we look into the dequeue function, you can see that it sets this t, which is the key object, as a result to this task completion source, which we have seen before here in this enqueue method. Here it creates a new task completion source and adds it to the queue. One thing I didn't understand at first was why we don't set the taken to true when we dispose this key object. But the reason is simple. It is not set to false, so it just stays at true. So when this new key is disposed later, it again is calling into this release lock, which then will check again if it was the last one, aka the queue is empty, and only then will it set this taken to false again. So it stays true until it completely worked through this queue. I found this async lock to be quite interesting. If you want to know more, you can peek inside this package yourself. The sources are also on GitHub. As for myself, I really like to use the semaphore slim approach because installing packages always comes with overhead for maintenance and maybe some package dependency hell that you might know when you're unlucky. And that's why I prefer the semaphore slim. But it's always interesting to see how it could be solved otherwise. And this Nito.AsyncEx package has many other async helpers that are really interesting to look into. The maintainer of this package, Stephen Cleary, is really quite the legend when it comes to asynchronous code. Anyway, guys, that was it for today. I hope you learned something new, and we will see us maybe next time. Bye bye.